Good morning all. Let us now go to the next part of the Lyapunov theory. So till the last lectures what we had seen was defining a Lyapunov function which can lead us to find the stability of a nonlinear system. So we had used the Lyapunov direct methods and indirect methods. In fact, for the Lyapunov direct method, it in fact centers around choosing a proper Lyapunov function which should be a positive definite function, that is v of x should be positive definite, and we went on finding out v dot of x and we checked whether v dot of x is negative definite or we went on finding out the definiteness of the function. But the problem here that we had faced was if we were not able to get a negative definite function or negative semi-definite function, we could not conclude that the system is unstable. So in fact, the Lyapunov function, the Lyapunov theorem is only a sufficient condition for checking the stability of the system. But if we get a proper Lyapunov function, it is one of the powerful methods for analyzing or studying the characteristics or behaviors of nonlinear systems. So in spite of all these difficulties, that is why this Lyapunov theory is being used for the analysis of nonlinear systems. Okay, so later on many methods were developed for the construction of Lyapunov function, which can lead to finding a negative definite function. Okay, negative definite derivative of the Lyapunov function. So we will see two methods. One is the Krasovskiis method and the other one is a variable gradient method. In this lecture, we will deal with the Krasovskiis method. So in this method, in Krasovskiis method, what we are going to see, we can consider an autonomous system here. X dot is equal to f of x and we have f of 0 is equal to 0 and x is an element of Rn. And this says that the equilibrium point is the 0 is the center. Okay, 0 points. Okay, then we know the Jacobian of this system. We know to form the Jacobian of this system, which is in fact this matrix dou f1 by dou x1 up to dou xn, and this is in fact this you have been doing a lot for analyzing systems. Okay, so now what is this? So I have v of x as we have x element of Rn. X is an element of Rn. Okay, now f of x is x dot is equal to f of x. Now let us choose v of x as something of this form, that is f transpose of x into f of x. Okay, f of x. Okay, so this for example, if I have x1 dot is equal to some x2 and x2 dot is equal to minus x1 plus x2 x2 cubed, what would be f transpose x into f of x? So it would be something like this, x2 into minus x1 plus x2 cubed into this form. Okay, x2 minus x1 plus x2 cubed. So this would be the square of this plus the square of this. So this in fact is a positive definite. This will be positive always. Okay, but there is a problem here. This can be 0 at times also. If this can be 0 at times also. We want the Lyapunov function to be a positive definite function so as to start our analysis. So the condition on f of x for the Lyapunov function to be a positive definite function is that f of 0 should be equal to 0. That means when x is equal to 0, f of 0 should be equal to 0, and also f of x, for f of x should not be equal to 0 for all x not equal to 0. So we should have only the equilibrium point at the 0, 0, 0 point. So this is one condition for v of x equal to f transpose x to be a positive definite function. So once we have defined this function v of x like this, we can apply the Lyapunov direct method here. So let us apply okay, we will apply the Lyapunov direct method here. So what we will have here is v dot of x is v dot of x, this is this x, v dot of x is equal to this f dot transpose of x into f of x plus, there is some problem with my pen, this is f transpose of x into f dot of x. Okay, so let us see what is this f dot of x. So we will do some kind of analysis here. F dot of x, what is f dot of x? That is dou f by dou x, dou f by dou x. The derivative of the function is equal to dou f by dou x into dou x by dou t. So this is in fact dou f by dou x. What is dou f by dou x? We know that this is a Jacobian, that is j of x into dx by dt is nothing but x dot. So it is nothing but j of x into x dot is nothing but f of x. So it is f of x. So our problem, there is something that we can use here. So what is f dot transpose of x? F dot transpose of x is f of x transpose into jx transpose. So I can write here as f transpose of x into j transpose of x. One second. So this is f transpose of x into j transpose of x plus, into f of x plus f transpose of x into j of x into f of x. The rest you can start doing now and try it out. F transpose of x, we can take this term outside and this term to the right, f of x to the right. So this can be written as j transpose of x plus j of x into f of x, So I can write this as f transpose of x into j hat, let me write it as j hat of x into f of x, where j hat of x is equal to j transpose of x plus j of x. Okay, so now what is the by Lyapunov direct method, what can you say from the Lyapunov direct method? We can say that if v of x is a positive definite function and if we get v dot of x as a negative definite function, we can say that the system is asymptotically stable. And if v dot of x is a negative semi-definite function, we can say that the system is just stable. Okay. Now, therefore, what should be the condition on j hat of x? J hat of x, if it is negative definite, right? If j hat of x function is a negative definite function, then the above system is asymptotically stable. So that is about the Krasovskiis theorem. So here, what is the idea here? The idea here is we are given this matrix here, the system here. We go on we will find out j of x, which is Jacobian of the matrix, Jacobian of the system, and then we will take the transpose of it and then add it with the Jacobian of that, and we will see what is j hat of x. And then we will go and check the definiteness, sign definiteness of j hat of x. We want j hat of x to be negative definite. This means that, this implies that we will see whether minus j hat of x is a positive definite function. Positive definite function. Okay, minus j hat of x is a positive definite function for all x. Okay, this will be a matrix. So we'll have to check for the positive definiteness, or for checking the positive definiteness, we can go and look at the principal minors of the system. Okay. And also there is one more important thing that we have to discuss here. We have been discussing about the 0 0 is the equilibrium point, right? 0 0 is the equilibrium point. We have been discussing about the stability near the neighborhood of the origin. Okay, so we say that the origin is stable, the equilibrium point is stable, and if we can extend this to the whole region, then we can say that the system is globally asymptotically stable. For that, we need another condition which is called the radially unbounded condition, which we had seen previously also. Radially unbounded condition. What is that condition? Unbounded condition. So what does it say? We have to check whether v of x tends to infinity as norm of x tends to infinity. Then we can say that it is a radially unbounded condition and this whole system is asymptotically stable in the large, or it is globally asymptotically stable. So this is the Krasovskiis theorem. It's quite very simple. You can try it out. So I will just state the theorem of Krasovskii. So this is what has been discussed now. So we are given an autonomous system here with origin as equilibrium point, and then j of x is defined like this. And if we have if we define j hat of x as a transpose of the Jacobian plus the Jacobian, and if we get j hat of x as to be a negative definite function in the neighborhood of the origin that we have defined, then the equilibrium point is asymptotically stable. In that case, we have the Lyapunov function. That means we have been trying to generate a suitable Lyapunov function for the system. So we assume that this is a Lyapunov function, and then we went on finding out v dot. From v dot we got this relation, right? So what can we say from that? We have got a suitable Lyapunov candidate for the system. So this is a suitable Lyapunov candidate for the system. So we have found out v of x as f transpose of x into f of x. And if we can extend this system, the stability norms, to the entire state space, then we can say that it is globally asymptotically stable. In that case, what we have to give the check is to check whether v of x tends to infinity as the norm of x tends to infinity. Okay, so this is the Krasovskiis theorem, and we also have a generalized Krasovskiis theorem, which also I have stated here. In case if a general statement comes like this, you may have to just change it a little bit. Instead of selecting v of x as f transpose of f of x, we choose what do we choose here? So we have this generalized statement here. So here, instead of choosing v of x as f transpose f of x, we choose it as f transpose p into f of x. So we define two positive definite matrices p and q, and we will get this relation minus q is equal to j transpose p plus p into j. This relation, this has been, in fact, in the similar pattern you can show that this is we get it in this form. Okay, instead of j hat we will get it in this form. Okay, so that's all. And here also the same case you can state that it is globally asymptotically stable for this condition. Okay, if it is valid for the whole state space. Okay, so now we will understand this problem a little more clearly by doing a problem here. So this is one problem here. So this is a system given here. What is the first thing that we have to check if we are going to apply the system? We have to see whether the origin is the only equilibrium point. Definitely here for the system, the origin is the only equilibrium point here, and we can choose v of x as equal to f transpose into f, right? And if we are going to choose v of x is equal to f transpose of x, something has to be true. What was that? We have to check whether f of 0 equal to 0 and f of x is not equal to 0. when x is not equal to 0. So this in fact this is true for the system. So for the system, because the origin is the only equilibrium point for this, so this condition is satisfied, so we can start our analysis. So what is the Jacobian of the system? So you can do that. You need not have to wait for me to do it, so you can start doing it. So dou f by dou x is like this. This is something like this. Okay, this is minus 1 1 1 minus 1 minus 6 x2 squared. Okay, that's it. Okay, so what is j hat of x plus j of x? J hat of x is equal to j transpose of x plus j of x. So this is nothing but, so this becomes equal to minus 2 2 2 minus 2 minus 12 x2 squared. So I can write this as, so what we have to check whether this is negative definite. In order to check the negative definiteness of this matrix, I will go and check the positive definiteness of minus j hat. I will go and check whether minus j hat is positive definite. Okay, I will also write it down here. Maybe later on I will write it down and before giving it to you. So before going, so I for checking the negative definiteness of it, I will go and check the positive definiteness of. We'll check whether this is a positive definite function. So how do we check it? We can, this implies we have 2 minus 2 2 plus 12 x2 squared. So in order to check the positive definiteness of this thing, what we can do is either we can go and check the eigenvalues of the system and check whether all the lambdas are greater than 0. Okay, greater than 0 for all x here. And here, or we can go and check the principal minors here. 2 is the principal minus, 2 is greater than 0. And also we can check the determinant of this 2 minus 2 here, 2 plus 12 x2 squared. And in fact, when you do this also, you will get it as greater than 0. So we can say that minus j hat is a positive definite function, which implies that j hat is a negative definite function. Fine, negative definite function. Okay, so from this, what can you say? What can you say? We can say that j hat is negative definite. So the origin is asymptotically stable. Asymptotically stable. Right. So what is your next step? We were trying to find out what is the topic. In fact, the topic is on construction of a Lyapunov function and also finding the stability of the system. So we will go and then find also the Lyapunov function here, v of x. Okay, so we can say v of x is f transpose of x into f of x. So what is that? So here you can write here, this is minus x1 plus x2 minus x1 plus x2, and what is that? X1 minus x2 minus 2x cubed, x1 minus x2 minus 2x2 cubed into this term, minus x1 plus x2, x1 minus x2 minus 2x2 cubed. So what you get here is this squared plus this squared. So you will end up with this squared plus this squared. This is a positive definite function. So you just calculate it and then reduce it and see, bring it into a very nice expression. That is what you can do. And then also in this case we can see that v of x goes to infinity as norm of x goes to infinity. This implies that It is radially unbounded, so it is globally asymptotically stable. Globally asymptotically stable. Really stable. Okay, this is about the Krasovskiis theorem. It's quite simple, but the next one is a bit involved. The next theorem and next method is a bit involved, which is the variable gradient method. Okay, so this are the references that I have referred. One is Nagrat and Gopal, and also Slotin and Lee, and you can also look into the video lectures, NPTEL video lectures, one of which I have given here, and there are also many videos on the internet. Okay, so these are, I have also referred the page numbers, so that means that you have to compulsorily look at the textbooks and read it. Okay, so that's about the Lyapunov construction, function construction using the Krasovskiis method. In the next class we will see the variable gradient method. Okay, then thank you.